So folks, as you noticed, we will record today's webinar and then we'll post it for folks who maybe won't make it, or for your, to be able to revisit at your leisure. So I guess you saw that we're now being recorded, and hopefully you're all okay with that. Give it another minute before we kick off. All right, let's get going. So welcome to today's Bridges-2 webinar, in which we will hear from Dr. Xiao Liang of PSC about high-performance GPU accelerated MuST software. Thank you for your interest and welcome. So this is a webinar organized under the auspices by the Pittsburgh Supercomputing Center, and this is our one-slide summary of what we've been up to since we were founded in 1986. And in particular, this is an event under the auspices of the Bridges-2 project, with which you're all familiar, I hope. And in particular, I would like to welcome you on behalf of our leadership team here. So I'm Sergio Sanielewicz, I'm the principal investigator. And so all of our team here welcomes you and appreciates your participation in this event, and we hope that you will benefit from it. So our Bridges-2 webinars, we basically started them up this year. This is the second one in the series, and it is a forum for the community to learn and share ideas and achievements. We have some speakers lined up, but we always welcome your suggestions for topics and speakers of interest, and work that is in progress, work that has been done. Please suggest, anybody can please suggest future speakers and topics, and that could of course be what you yourself are working on. And you can just email me and I will make sure it gets considered, it gets the consideration it deserves. So today we are happy to hear from Dr. Xiao Liang. He holds a PhD in physics from the University of Science and Technology of China, and after some postdoc stints at USDC and at Tsingtao University, he recently joined PSC as a postdoctoral researcher to work with Dr. Yang Guang, who's here in the audience. He's one of our team members, specifically to work on the code he's going to be talking about today, which is MuST. And specifically, this is a code that is being prepared for the NSF leadership class computing facility that we hope will come online in maybe 2026, 2027 in Texas, which is going to be roughly 10 times the power of the current Frontier system at the Texas Advanced Computing Center. So Yang has a grant to work on that, and Zhao will be working with him on that. But as you see here, Zhao has more general research interests. And so we're all very happy to hear from him. And I think a particular focus, which is probably of interest to a lot of us, is to how to use multiple GPUs in parallel on a single job. Finally, before I hand things over to Xiao, here are some logistics for today. So all of us except Xiao will be muted during his presentation. Please type your questions into the Zoom chat. Yang and I will be monitoring, and Yang especially might be able to address some of the questions right there in the chat while Xiao is presenting. But when Xiao finishes his presentation, then he will he will see the questions there and open up, and he will answer questions live at the end. And then for any remaining questions or follow-ups, Xiao has graciously agreed to take them just by email to his own email address. And I'm sure everybody appreciates, as we do, the email address that he chose. So with that, without further ado, Xiao, the floor is yours.
Okay, let me share my screen.
Yeah, so you can now share your screen. Yeah.
Oops.
Looks good.
Okay. Should I start now?
Yes, please.
Okay. Good afternoon. Thank the host for the introduction, and thank the audience for your time to join this webinar. Today, I will introduce our recent work on improving the performance of the MuST software. Before my talk begins, I would like to introduce the software package MuST, which is currently open sourced on GitHub. MuST can do the electronic structure calculation based on multiple scattering theory, along with the Green's function technique. This is a different approach comparing to widely used software package like VASP, Expresso, Win2K, and so on. The MuST is under active development. If you are interested, you can download the code, compile, and run. I will also introduce the procedure for combining and running the GPU-accelerated version of MuST on Bridges-2 in this talk. This talk focuses on the GPU acceleration of MuST software. This work involves contributions from the Pittsburgh Supercomputing Center and the Texas Advanced Computing Center. We conduct tests on facilities from both institutions. I appreciate their involvement. My talk will be divided into 8 sections. Firstly, I will introduce the density functional theory in the formation of single particle shorting equation. Then I will introduce the Green's function approach to solve the single particle shorting equation. And this method is called the KKR method. I will also introduce the concept of a linear scaling method, the LSMS, based on the KKR method. And this method has won the Golden Bear Prize in the year 1998. Then I will introduce the computational challenge of the KKR method and the LSMS, which is essentially the large matrix inverse. I will present the GPU-accelerated matrix inverse for the master software. Our performance benchmarks were carried out on several HPC facilities from TEC and PSC. Then I will demonstrate how to run GPU-accelerated MuST on Bridges-2. In the end, I will raise some outlooks. Okay, we start from the basics of density function theory. To understand the physical properties of a given material, one is to determine the electronic structure which is the quantum states of electrons in the material. If one tries to solve the exact Schrodinger equation, which is a quantum many-body problem that a type of quantum computer today claims to solve, the problem arises due to exponential growth of degrees of freedom. Fortunately, the density functional theory tells us that there exists an equivalent system that has the same energy property, but easier to solve. In this equivalent system, electrons are moving independently in a fictitious external field. Because of this independency, the Schrodinger equation is greatly simplified to a one-electron equation. The fictitious one-electron potential, Vxc, in the equation depends on the electron distribution in the entire space. The commonly used approach to the potential is to apply the local density approximation, that is, the potential at a given location depends only on the electron density at that spot. Based on the fictitious one-electron potential depends on the local electron density, and the potential also determines the electron wave function, as the charge density is directly obtainable from wave function. Thus, the electron wave function can be solved self-consistently. This diagram denotes the procedure for self-consistently solving the single electron equation. You can start the procedure by assuming an effective one-electron potential, then solve the Schrodinger equation to obtain the wave function. With the wave function, we can obtain the charge density. Then we can construct the effective one-electron potential through LDA or GGA. We then have a new potential, and the previous potential is substituted with the new one, and we solve the Schrodinger equation again, and such procedure is repeated until the solution of the Schrodinger equation and the one-electron potential converges. The one-electron Schrodinger equation is solved to obtain the wave function, and the wave function is represented in a basis set. Because the wave function oscillates violently near the nuclei, large number of bases is required, and the pseudo potential is a much smoother effective potential, which makes the basis number manageable. Here, we start from a different approach, comparing to directly solving the one-electron Schrodinger equation. Let me recall the Green's function of the Hamiltonian. If we have a stationary Schrodinger equation for the single particle case, with H0, the kinetic term, and V, the potential, and based on the definition, we can construct the Green's function for the free particle as G0, and the Green's function for the particle in potential as G. When the free particle and the particle in potential have the same energy, such as the E here, we can construct the wave function in potential through the free particle's wave function. So this is the wave function in potential, and this is the free particle. With the wave function in hand, we can obtain the charge density. And this formula can be rewritten in the formation of single-site scattering matrix. However, based on the definition of Green's function, the charge density is obtainable without knowing the wave function. When we write down the Green's function that connects the position R and R prime, based on the definition, the density is actually embedded in the numerator, and we can extract the charge density through the integration on the imaginary part of the Green's function by setting R and R prime the same. Therefore, once we obtain the Green's function, the charge density can be solved without knowing the wave function. As the effective potential in the single particle Schrodinger equation only requires the charge density, we can solve the charge density using the Green's function without solving the wave function. The previous slide introduces the Green's function for the single atom site. What if there are more than one atom in the unit cell? When the electron is placed on the potentials introduced by multiple atoms, there is a formula calculating the Green's function on each atom site. Well, in the formula, Z and J are solutions of the Schrodinger equation on one atom site. The information of potentials introduced by multiple atoms is contained in the multiple scattering matrix, the TOR, and it is solved in the framework of multiple scattering theory. The TOR matrix is solved through the inverse of the so-called KKR matrix. The KKR matrix is built through the Dyson equation, while T is the single-site scattering matrix mentioned in the previous slide, and the G0 is the free particle propagator between two different atom sites. In the KKR matrix, each diagonal block is the inverse of a single-site scattering matrix, and the non-diagonal elements are just the free particle propagators. This matrix is constructed considering all the atoms in the unit cell. Thus, the rank of the matrix is proportional to the atom number. The rank of the KKR matrix is the atom number multiplies the basis number in each atom site. If spin is taken into consideration, the rank size doubles. Compared to directly solving the wave function, the KKR method has several differences, or namely advantages. Because the wave function is not solved, pseudo potentials are not required, and we do not need to manipulate the wave function, and we don't diagonalize the Hamiltonian. Instead, we compute the inverse of the KKR matrix. And the Green's function can be added linearly. Thus, the KKR method can be used for studying random alloys with the help of CPA. Okay, let's do a brief summary on the KKR method. Firstly, we need to solve the single-site solution Z and J, and the single-site scattering matrix T, and the free particle propagator G0. Then we build the KKR matrix using these elements, and then we invert the KKR matrix to obtain the multiple scattering matrix TOR. And we construct the Green's function with TOR, Z, and J, and we obtain the charge density through the Green's function by the integration on the imaginary part of the Green's function. Once we have the charge density, we can rebuild the effective potential using either LDA or GGA. Once a new effective potential is built, we need to solve the charge density again until the charge density and the effective potential converges. On the aspect of solving the one-electron Schrodinger equation, either the KKR method or directly solving the wave function is equivalent, as both methods aim to solve the charge density. This is a diagram illustrating the self-consistent procedure for KKR method. We start by assuming an effective potential for the crystal and solve the Green's function. Through the Green's function, we then have the charge density on each atom site. And a new effective potential is built with the charge density through LDA or GGA. Then we go to the self-consistent procedure. Next, I will introduce the linear scaling method, the LSMS. Considering the charge density on one atom site, for example, the atom I in this slide, the charge density is obtainable from the Green's function, and based on the Green's function formula, Z, J are all single atom site solutions. The information of multi-atom potential is in the multiple scattering matrix TOR. In the original KKR method, the Green's function is obtained by considering all the atoms in the unit cell. However, when an atom is too far away, its contribution to the TOR matrix is negligible. Therefore, when building the TOR matrix, we can consider the atoms in the region within a specific distance from the atom that we are considering. And each atom has such a region. And the region is named as the local interaction zone, which is the leads in the slide. In this way, the Green's function on each atom site is obtained by building the KKR matrix by only considering the atoms in the leads. When the lead size is fixed, the rank of the KKR matrix is fixed. This method is called the locally self-consistent multiple scheduling, the LSMS. Unlike in the original KKR method, in LSMS, the size of the KKR matrix does not grow when increasing total atom number in the unit cell. The computational cost is the inverse of the KKR matrix for each atom in the unit cell. Therefore, the LSMS is linear scaling with respect to total atom number in the unit cell. As introduced, either the KKR method or the LSMS method, the important part is calculating the Green's function, while the Green's function is obtained through the multiple scattering matrix tau, and the tau matrix is obtained through the inverse of the KKR matrix. So the major computational challenge is the inverse of the KKR matrix, as each element in the KKR matrix is a complex number with double precision real part and the imaginary part. The matrix inverse essentially can be accelerated by multi-core, either in a multi-core CPU or the acceleration card with many small computing cores, such as the GPU. In this slide, I will explain the multi-core acceleration by briefly introduce how the matrix inverse is performed. The matrix inverse is essentially solving a system of linear equations, such as solving the vector x under AX is B, where matrix A and B, matrix A and the vector B are previously known. The first thing is performing the LU decomposition of matrix A into two trigonal matrices, where L is the lower trigonal matrix and the U is the upper trigonal matrix. Trigonal matrix is good. As denoted in this slide, when solving the vector y for Ly is m, because L is triangular, it is straightforward that y1 is 1 and y2 is 5 minus 3 times 1. Therefore, each element of vector y is obtainable sequentially. When solving the vector x for the linear equation ux is n, as u is the triangular vector x can be solved in a similar way. Therefore, when solving the vector x for ax is b, if we regard ux as a new vector y, then y is solved in this fashion. Because we have y and x can be solved in this fashion. The matrix inverse is solved by solving several systems of linear equations, as denoted for the 2x2 matrix case in this slide. In the process of solving linear equations, there are many matrix multiplications which can be accelerated by multi-core. Here, I present a speed test of the MuST software. We want to test the portion of matrix multiply when running the MuST. Because matrix multiply is scalable on multi-cores. When calling the LabPack functions, it will parallelize the calculation by utilizing the threads. Therefore, without modifying the code, we simply setting the OpenMP thread number larger than 1 and compare the running time. The testing results show that the MuST software can be efficiently accelerated by multi-core. Based on the OpenMP thread test, we will offload the matrix inverse calculation on GPUs, and we expect high acceleration ratios. Recalling the Green's function formula, as we are caring about the charge density per atom, we only need part of the tau matrix. For the Green's function on nth atom site, only the nth diagonal block of the tau matrix is needed. Therefore, we can use a block LU algorithm instead of inverting the whole KKR matrix. This is the procedure of the block LU algorithm, which is already implemented in the CPU matrix inverse in MuST. We firstly divide the matrix to be inverted into 4 blocks. We know that the inverted matrix on this block is obtainable. we continue calculating the matrix inverse by further dividing the matrix into four blocks. And each step reduces the size of the first block. The stopping criterion is when the size of the first block is reduced as the necessary block size. Comparing to the cubic scanning of matrix inverse, this recursive method only requires the squared scanning, thus is more efficient on CPUs. However, as the matrix inverse can be highly accelerated on GPUs, our implementation is sending the whole KKR matrix into GPU and invert the whole matrix on GPU. Then we retrieve the nth diagonal block of the inverted matrix from GPU. The master software is written in Fortran programming language. Until now, there are several implementations for calling CUDA functions in Fortran programs, like the NVIDIA HPC SDK. Such SDK simplifies the programming for calling the CUDA functions, especially for future computing architectures that the data transfer cost between CPU and the GPU is much lower. However, in our case, there are intensive data transfer between CPU memory and the GPU memory. To make the data transfer manageable, we call the CUDA functions in a separate C written program, and we use the Fortran-C interface to call the C program as a Fortran subroutine. As denoted in this slide, when we need to inverse the KKR matrix, after the KKR matrix is built, we determine where the matrix inverse is performed. If on CPU, then block LU is adopted. If on acceleration cards, we initialize the variables in a Fortran subroutine. Then we call the C program through the Fortran-C interface. Here, we demonstrate the Fortran-C interface. In the Fortran part, it's just a subroutine calling the C. In the C part, there are four kinds of operations. Firstly, we need to allocate the GPU memory. Then we copy data from CPU memory to GPU memory. Then we do the LU decomposition and solve the linear equation to inverse the matrix using cool solver functions. Then we copy the calculated data from GPU memory back to CPU memory. Okay, next I will present our test systems and the test results. Our matrix inverse is double precision calculations. Double precision calculations can be nowadays, double precision calculations can be performed on the NVIDIA V100 or A100 and the AMD Instinct series acceleration cards. We tested on HPC systems on the Texas Advanced Computing Center and the PSC. This is the Lone Star system in tech, and you can see that the computing nodes are liquid cooled, and each GPU node is equipped with 3 A100 40GB GPUs. This is the Bridges-2 in PSC, and each GPU node is equipped with 8 V100 GPUs. There are two kinds of GPUs. One is 16 GB memory, and one is 32 GB memory. Another is the Brain Information Library cluster in PSC. The GPU node has 8 A100 80 GB GPUs. In general, we tested on 4 kinds of GPUs. The V100 with 16 GB and 32 GB memory, the A100 with 40 GB and 80 GB memory. Let me present the acceleration results. In this testing case, the rank of the KKR matrix is 12450, and inverting the matrix this large will be significantly accelerated on GPUs. Here, the baseline of the acceleration ratio is the CPU case with 32 MPI ranks. Here, MPI rank number is the CPU core number. The MPI processes are evenly distributed on multiple GPUs when GPUs are involved. As depicted, GPUs can accelerate the calculation. If we use all the 8 A100 GPUs, the acceleration is more than 10 times. If we look at the cases under the same GPU number. Increasing the CPU number leads to higher acceleration ratio. For the cases of both 4 GPUs and 8 GPUs, 16 CPUs are roughly 1.5 times faster than 8 CPUs, and 32 CPUs are roughly 1.2 times faster than 16 CPUs. If we look at a case under the same CPU number, and increasing the GPU number also leads to higher acceleration ratio. For the cases of both 8 CPUs and 16 CPUs, 8 GPUs are roughly 1.2 times faster than 4 GPUs. However, where there are 32 CPUs, 8 GPUs is roughly 1.4 times faster than 4 GPUs. The conclusion is that more MPI rank number, as well as more GPU number, will accelerate more. However, there is an optimal configuration of MPI process number on each GPU, and such optimal configuration is definitely related to the size of the problem. The table below depicts the detailed data, and this is the number of GPUs, and this is the number of CPU cores. The number in the brackets is the portion of the time for GPU data transfer and GPU compute. The data transfer takes roughly 10% of the total GPU time. Nowadays, a CPU node can have as many as 128 CPU cores. The 8 MPI process on 2 A100 GPUs is as fast as 128 CPU cores. Next, I will demonstrate running the GPU version of MuST on Bridges-2. There are 3 kinds of GPU nodes on Bridges-2. The 8 V100 with 16 gigabytes and 32 gigabytes memory, and the 16 V100 32 gigabytes memory. When combining the master code on GPU nodes, we need to find the suitable math library for the CPU. On Bridges-2, all GPU nodes use the Intel CPU. Therefore, we can use the Intel MKL. Combining MuST needs to set up the environment first. On Bridges-2, we can module load the necessary libraries like the MPI, the CUDA, and the Intel MKL. Both OpenMPI and Intel MPI works. After setting up the environment, we can download the source code of MuST through the clone and try to build it. This is the architecture file used for combining MuST with CUDA acceleration. The important things are setting the acceleration flag to 1 and then linking the CUDA libraries. Furthermore, we need to set the GPU compute capability here, because the proper compute capability will fully utilize the GPU. There's a GPU demo in this directory, which is contained in the official MuST repository. And this is a demo submission script for, as the audience are mostly Bridges-2 users, the submission process is familiar. A major difference is that we need to use a bash script to bind the MPI process on different GPUs. We can execute this script while executing the MPI run. You can also specify the GPU number in this script. This will evenly divide the MPI ranks on multiple GPUs. Lastly, there are some outlooks and our future directions. In future, we can reduce the cost for data transfer between CPU and GPU by constructing the KKR matrix on CPU. And until now, the matrix inverse on each MPI process is performed on single GPU. When we have a large number of GPUs, we can also perform the matrix inverse on multiple GPUs, which can further increase the KKR matrix size. Although all our tests are performed on NVIDIA GPUs, and other vendors also deliver similar products that is promising to deliver competitive performance, Thus, in the near future, we will test our code on other acceleration cards. And until now, all our calculations were performed under the muffin-tuning approximation. The acceleration of full potential acceleration is one of our future directions. Lastly, thank you for your attention. Besides the contributors, I appreciate the useful discussions with Marcus, Vishnu, and Mike Whitten. And we also thank Todd Pike at PSC for setting up the access to the brain image library GPU node. We also thank Dr. Junjie Li at Tech for providing his tool to provide the master code on tech systems. Thank you very much.
Thank you very much, Xiao. And I think we have plenty of time for questions. Yang has already answered 2 of them in the chat, so you guys fire away. You can either type it into the chat, and or you can just directly raise your hand, and Xiao will take your Xiao, you'll take your questions live.
Okay.
Any questions? Okay, Sagnik asks, what was the benchmarking tool used?
Benchmarking tool. We just what we do is that we log the war time, the running time. We compare the running time of each subroutine in Fortran. We can log the time.
Maybe the question also is like, how do you measure the communication ratios and things like that?
All our tests are
Which
done
included in the table, right?
Okay. Firstly, our benchmarks were done on a single computing node, so there is little communication, and now we are focused on the portion of the time for each function implemented in MuST. So that's easy. We can log the time and print them out. Also, in previous slide, we do the OpenMP test just to see the portion. Is there a large portion for matrix inverse in the master calculation? And the answer is yes. And we also log the portion of the time for just the matrix inverse and the total running time. So that is our benchmarking tool.
More questions, please. So Yang or Zhao, maybe you can tell people, you know, how they could get to run MuST on Bridges-2, say, and you know, try things for themselves.
Okay. So this is basically the procedure. So you download the code, and you edit the architecture file. So there is a demo architecture file, and you edit this architecture file linking to the proper libraries, and you combine the code. And after you combine the code, and you can run the demo here. So there is a demo in this directory. And when you submit into the GPU nodes on Bridges-2, you should consider how many GPUs you will use. And the important thing is that you should divide this MPI processes into this multi GPUs. So you need to include this script file. It's also included in this location. So then you can run the code, and yes, this is basically the procedure.
And I also think, right, Yang, that there is, like in the Bridges-2 user guide, for example, there is documentation about MuST, and that, you know, because it's an NSF project also, you have, because like maybe people want to adapt it to their own use and use it on their own problem, but all of that is explained somewhere, right, Yang?
Yes, there's a wiki page on GitHub. You can once you get onto the GitHub for MuST, there's all the explanation. There's documentation. When you download the code, there's a document directory. It has a user guide, shows how to run code.
Okay. Thank you. Any other questions today? If you think of something in the coming hours, days, I think Xiao has agreed to look at your questions and interact, right, Xiao?
Yes, sure.
Okay. You want to, I think we provided your email address, but if you want, you could type it into the chat so people have it.
Okay.
There you go. Well, if nobody has further questions, I think we can get done here and start thinking about what we just heard. Final call for questions. Oh, there you go. We have one.
No, sparse matrix is not they are all dense matrix.
Okay, let me answer this question. For the QKKR method, matrix are this dense matrix problem. But there is a one version of KKR. It's called a screen KKR. In that case, we can form a sparse matrix. Yeah, so far we haven't implemented that yet, but that's on our agenda. That sometime in the future, when we implement sparse the screen KKR, then we will have issues about how to invert a sparse matrix. That's kind of things in our to-do list.
And are there specific physical systems, physical problems for which the sparse version would be more appropriate?
Well, basically, screen KKR allows for deal with much bigger systems. Instead of doing LSMS, you can do a screen KKR. That's one of the kind of very unique technique about KKR method. There are some already publications if you want to know a screen KKR. There's a unique application for that.
Does anybody want to see maybe a link or something in the chat?
Well, there's a couple more questions.
Well, Mitchell's is just a recommendation, but okay. You see the one from Bintang?
Yeah. I think a novel numerical linear algebra technique is NASA utilizing. Yeah, I guess what's the unique about the linear algebra technique? For example, we do this blocking method for increasing the big matrix, and we only take, because our interest is only the final result is the upper left corner of the block. So that kind of technique we considered. We find that's really reduced the number of operations by quite a big factor. We haven't considered other techniques. If you know something that would recommend, we'll be happy to take a look. Thank you, Bintang. Thank you for the question.
Okay. Any more questions? One new message.
Summarize answer. Oh, I'm sorry. Xiao, you might be able to answer. Would you say that? Yeah, just say that again. And
Okay.
You can ask directly. I think you can unmute now, Bintang, and just talk to Yang and Xiao. I think Bintang just wanted you, Yang, to repeat what you said about the linear algebra.
I
But
think
yeah, okay.
basically, yeah, the linear algebra part, the technique we use is in Xiao's presentation about the blocking technique.
Yes, the block technique. Let me go
Yeah.
to that slide.
Yeah.
Okay.
Yes, this is a block inverse technique, but it's not used on GPUs. Because on GPUs it is actually not efficient. On CPUs we use this technique. On GPUs we just use the whole matrix inverse. So it's much faster than this implementation.
Yeah, the thing is, we are only interested in the inverse of the final the upper left corner block of the inverted matrix. So in principle, we don't need to invert entire matrix. So the technique here is we start by dividing the matrix into 4 blocks, where A22 is a smaller matrix, smaller block. So we just kind of keep on going recursively, going towards the upper left. So every time we do an inverse is a smaller matrix here, using this kind of recursive technique. But that involves a lot of matrix multiplication and but inverting a smaller matrix.
Thank you. All right, final call for questions. And again, if you don't think of it now, you know where to send them. Okay, well, thank you very much, Xiao. Thank you, Yang, for your interventions. And thank you, everybody, for attending. And we hope that has been useful. And we will see you again next month when we will have another exciting webinar that we will be announcing. Thank you.
Okay, thank you.
Bye-bye.
Bye-bye.